It gives me some flashing red lights, so, yeah. Okay.
Is it really?
Yeah. Well, it looks like we're in business one way or t'other. So I've been here and talked about gas chromatography. You probably had liquid chromatography in here. Okay. And I'm going to get to mass spectrometry. So, the two chromatographic methods are basically involved in separating compounds. So doing a separation for quantification, whatever you want. Mass spectrometry really is there to identify compounds. They have some powerful ability to also do identifications, quantifications, function as a gas chromatographic or an LC detector. So it's really a useful, fairly flexible tool. The primary purpose is to identify compounds and whether they're known or unknown. I probably shouldn't have put unknown. You might be looking for a known compound someplace. So anyway, but basically to identify compounds. When you think about gas chromatography, what information do you get from a gas chromatograph? You get a line on a piece of paper. And what is that? Well, I have no idea what that is based on gas chromatography. But mass spectrometry then takes care of that. So whatever comes out of a gas chromatograph can be fed into a mass spectrometer. What comes out of an LC, what can also be fed into a mass spectrometer. Then we get a lot more power. And then while I say to identify unknown compounds, that's certainly part of it. But you also can get a good deal of information, both quantitative information and structural information from mass spectrometry. So it's really a tremendous tool that's come into being and probably is getting pretty close to maturity. Like it's not going to get much better because they've taken all the easy stuff or good stuff out of it. So anyway, that's what we'll spend our time on today. If, of course, we go to the next slide. Okay, guys. Neither one of the arrows do anything. The enter key doesn't do anything. I'm not going to push the terminate button. That one would probably work, right? That'd be the end of us. Okay, which one did that? The space key? The bar key?
I think you just had to click on the slide and then go. So were you here or now?
Looks good.
Okay, sweet
to me. Okay. And so here are some of the applications that mass spectrometry is used in. And just chosen things to show diversity. The idea of looking at our athletes using steroids. So drug use, for example, nothing better, nothing more sensitive, nothing more certain than mass spectrometry for that. Monitor the breath of patients by anesthesiologists during surgery. So you'll see a mass spectrometer in potentially a surgery office or surgery facility. Determine whether honey is adulterated with corn syrup, locate old oil deposits by measuring petroleum precursors, monitor fermentation, detect dioxins and contaminated fish. You can go down the line, determine if horses are given cobra toxins to perform better in a race. And so it's absolutely fascinating the number of uses that mass spectrometry has found. We'll spend the first lecture on kind of hardware. What is mass spectrometry? How does it work? And then the second lecture will be more applications than the other sections. So we'll get into applications. Principle of operation. Okay. What we really need is what we call a source. And the source is basically what's the source of breaking a molecule down and producing a whole family of reaction products. And so what you do is you really input a good deal of energy, like I say, and the molecule literally explodes. And the weak parts are where the breakdown, the strong parts of a molecule stick together. So you get pieces, you get bits and pieces that are very reproducible. You bombard energy, you get the pieces. If the pieces fit, okay, you've got an identity. So it's the source is a very important part of it. Like I say, that's where we blow the molecules up and look at the bits. the mass analyzer takes all those pieces that the molecule got blown into and separates and kind of draws a detector line on. It's just the third part goes into the detector. So you separate these fragments, you detect them, measure them, and that's basically what you look at in the system. This is I like this figure because it's kind of pretty. It's got nice colors and it's very clear, but it's not actually what's in use today in one sense. Up here we've got the mass analyzer, and we say a magnet. So what you do is over here, that's where your effluent from a gas chromatograph comes in. That effluent goes under a high electron beam, powerful, very that's where energy comes from, blows it into bits. And then we want to separate those bits so we can measure them one by one by one. So we need to separate all those fragments we just blew the molecule into. And in this case, there could be a magnet there, and that's correct. The earliest machines, there was a magnet. And there's something about electric charge moving through a magnetic field exerts a force on it. And so kind of the laws of nature take over here, and you can then separate each of these ions into one at a time, coming down and going through the reagent masses and come down here and detect them. So the magnet, that was the first one. What you find now is a quadrupole. That's how, so we blow everything up and the quadrupole separates these fragments into pieces that can be counted. So it's a nice picture in that sense, and it's exactly correct. There is a detector, there's a source over there, and there's a way of separating these fragments into bits and pieces. So again, that's the section that's now been replaced. There's several ways that you can separate these fragments into, proper classifications. And magnetic sector, like I say, was the first of its kind, and we've gone on to measure some other ones that you'll see. So this is the pure compound ideal is fed into a mass spectrometer. The mass spectrometer doesn't, the one part of it where all the work goes on, really doesn't separate compounds very well. So we get our separation taking place first. So principle of operation, pure compound, this idea is introduced to the mass spectrometer. That can be a little microgram or milligram, whatever material, put on the end of a probe. That probe can be put down into the instrument and bombarded with energy, blow it into bits and do separation. Direct probe, we don't tend to do that much anymore. If we were doing something very specific and we wanted just to look at one thing, we might do it, but we don't typically do the direct probe. That's only for pure compounds. We typically work with effluent from a gas chromatograph. So we put this as a detector on the end of the gas chromatograph or an LC. So we get our separation from the GC and the LC. And so we don't need the direct probe part of that. So that's our separation. So we put a molecule in, we blow it into bits, and we start sending out those bits and pieces. Okay, here's piece 1, 2, 3, 4, 5, and we can separate them and basically bombard them with energy. And you'll get the pieces to look at. It is high energy in the source, good fragmentation, so we can get a lot of pieces to put together to identify compounds. There's a disadvantage. So if we look at the electron ionization source, high energy, low energy. High energy is most common. That's, like I say, coming off of an LC or GC, bombards with high energy, get lots of pieces. So you got lots of pieces that are unique, specialized, that help you in terms of identification, quantification. It does blow it into pieces, a molecule into pieces, and sometimes then one of those pieces isn't the intact molecule. It's all been blown completely into pieces. And we like to see what we call the parent ion. We like to have a molecular weight of a compound. That's kind of important when we start looking at putting things together and trying to say, what is this? If we know its molecular weight, that's a real helpful metric to have. So in fact, we don't see a parent ion, and we may lack some sensitivity too. So They're good. They're the very broad source of mass spectrometry. Probably the most common use by far is using this high energy, blow the molecules up approach. If we can put in low energy, then what we want to do is we just want to knock off maybe one electron or something like this. So our mass, it gets a charge, but a very little charge. The molecule is intact. So high energy, we blow it to bits. Low energy, we don't want to blow it to bits. We just want to put a charge on the molecule so I can get a molecular weight. And then I can use that for other purposes. So notice low energy is more sensitive. When you blow it into a whole bunch of pieces, you don't have a whole lot of any one of those pieces. If you just do it with the molecular weight, the intact molecule, you've got a lot of that or much, much more. So sensitivity suffers some. So parent ion, like I say, that's what oftentimes people use, or a term that's used in discussing the fragmentation, blowing apart. And they also call it molecular ion. The base ion or base peak, because this draws something, it looks like a chromatogram, for here's this ion, and so on. And so the base peak is the most abundant fragment, the most abundant piece of that molecule. And we'll see some examples of these, so kind of go through what they are and how they're used. And so this is the most abundant ion as it draws out, the picture of the fragments that this blew into. The most abundant peak, that's the highest peak, the most abundant there. Then everything is kind of rated. How much of each of these fragments are we finding? So what are the fragments? What are their molecular weights? And how much are formed? This is the information that you collect from this. This is an example of fairly simple chloroacetylphenone. It's a molecule, the typical spectrum from that. It's rather unique in that it's not so messy. So our compound is in the middle up there, are two phenyl groups or benzene rings, the C double bond O and a chlorine on the end. So that's our starting molecule. Bombard it with energy, it tends to go to 1, 2, 3, or 4 primarily different products. And they will tend to show up down here. So this fragment here says 7077. That's a benzene ring, lost one charge. And so that's the amount of that particular fragment of this molecule that's present. There's 105 here. 105 is a benzene ring with a C double bond O, like in the center up there. And so what you're seeing, this is a tabulation. So what fragments are here and what's the abundance of each of these fragments as you go along. And you put that data into a computer, a search, a library, and you come up with names. So what is this compound? It's a very powerful tool for doing that. We have a choice of how much energy we put into the system. Very commonly, it's 70 electron volts. That's more powerful than most ions that you'll form, any bonds that you'll form. So if you hit it with 70 electron volts, which is high energy, what you'll find is you get a lot of pieces. This molecule, its molecular weight, this is pentobarbital, its molecular weight is 226. But what do we see? Do we see anything up in here? Not really. We hit it with high energy, blew it to bits. And so we see something lower mass. Here we decided, well, let's not blow it into quite so many bits. And so we see we've got 157, 185, and then the mass of the molecule is 226. It shows up as 227. It picked up one electron, one charge. So you can run low energy if you want to see what's the molecular weight, what's the most abundant fragment. You use high energy if you need more information. I want to see all the pieces. I got to put this darn thing together. This doesn't tell me too much about the pieces. That tells us much more about pieces. So it depends on what you're doing, quantification, or you're doing identification of how much energy you use in blowing this molecule apart. There's many different ways to ionize a molecule as it comes out of an instrument, GC or LC. One technique is called MALDI. matrix-assisted laser desorption ionization, and we'll talk about each of these. ESI, electrospray ionization, DESI or DESI, direct electrospray ionization, DART, direct analysis in real time, and FAB, fast atom bombardment. So different techniques, different ways to do this ionization to get that energy into that sample. So looking at that MALDI, so we typically, or most commonly, we put our molecules in as pure molecules and they get bombarded and blow into bits. But there's sometimes a benefit in assisting that breakdown. And so what you'll do in some cases, you'll put a sample into a glue or a matrix, whatever. And when it gets hit with energy, it kind of expands. It kind of helps break down the molecule into pieces. So matrix assisted breakdown is what I could call it. So that'll help us break down the pieces to get a better analysis. And that's used on very high molecular weight molecules. And so things like proteins, peptides, glycoproteins, oligosaccharides, basically they need that MALDI. They need that matrix to blow into pieces. And so that's, like I say, what's used in forming ions for large molecules. The recent application is with using that technique is actually came in my area, looking do flavor molecules chemically bond onto proteins? Is that where my flavor went? Part of my flavor got chemically bonded on. And so this basically is a technique that I find very, very useful. I'll show you some kind of examples of that part a little later on. So sample is pre-mixed with a high energy absorbing matrix. So when it gets zapped, okay, matrix takes it up, transforms a laser, so laser energy into excitation energy. And basically the analyte gets ionized with very little decomposition. You usually are aiming for molecular weight, what we call the parent ion. So this matrix is really good at giving us a parent ion. So the molecule that's intact. So this is kind of an illustration of that, where we've got a high voltage over here. We've got that purple, that's purple, blue, whatever, kind of circle there. It gets bombarded, where your sample's in there. It gets bombarded, blows into pieces, and it goes across the same usual, separating the pieces that this molecule blow into and gets detected. So kind of the process of the MALDI. When we use that a lot. Like I say, you'll see some examples a little bit later. So it's soft ionization process, little fragmentation, easy interpretation of data. Typically 1 charge per unit mass or unit molecular weight. It is limited in molecular weight. We only put 1 charge per molecule. If that's a big molecule, that 1 charge doesn't help us too much. We need many more charges on it so we can grab it and drag it down this pathway. So it is limited in terms of molecular weight. So works well up to maybe 2,000 molecular weight or so. It gets a little tougher after that. This is showing protein analysis. So what do we have over here? We've got our molecular weight of our protein. It's fairly small, 2,466 molecular weight. We put this into our mass spec. We get some matrix in there. So this is our matrix breaking down, and that's our compound breaking down. So transfer energy here into there to give us a molecular weight. The molecular weight is an important metric for us oftentimes. This is, again, another example of beta-lactoglobulin. And so we find beta-lactoglobulin. So that's a nice real protein. We get the 18,317. That's basically molecular weight of beta-lactoglobulin. But there's other things that get attached to it in life. And so we also are seeing other molecules. Here's another molecule attached to it, another one. But this mainly, if we looked at purity, it's mainly the beta-lactoglobulin with a little bit of other things. And so it's a nice example of looking at a molecule that has a mass of over 2,000. This is vanilla or vanillin has been reacted with beta-lactoglobulin, so vanilla. And what we find in that case is that we'll actually get the parent ion over here, so our plain pure compound there. But here, this one's reacted with vanilla. And so whatever amount of protein is reacted with vanilla, it actually bumps up and we've got a second curve for it. So we know how much protein wasn't chemically bonded and how much was chemically bonded to our flavor. It's one of the problems that you face when we look at it working with proteins. Proteins like our flavor molecules. And there goes our flavor, and very quickly or a longer storage problem. So it's been a really useful technique to look at flavor interactions. This was looking at an alternative now. So that was number one. Here's fast atom bombardment. And so in this case, you're again using a secondary chemical to interact and to pass on its energy. So similar in many ways, but just slightly different mixture in how it's done. The ionization, the particle beam transfers energy to the matrix, and light's ejected off the surface. Okay, secondary ions. We won't bother to that. This is a picture that shows MALDI. And so the MALDI, we've got our analyte in our matrix here in the orange. And then there's the atom beam, so atoms coming in and high energy atoms, they collide with this matrix on top and form a number of products of this collision, this basically explosion. And so what we do is those fragments, some of the pieces that blows into are positively charged, some are negatively charged. We only measure the positive. So we've got a negative charge on these focusing disks above in the blue. So we're dragging those up. We're going to put them into the mass spectrometer, do our sizing, counting, and for quantitative purposes. Very, very useful technique. There's another one. I don't know. Anybody been to an airport ever? Anybody take a swab of luggage and bring it over? And well, that happens. And so what they're looking for is gunpowder, explosive, any kind of thing that maybe you wouldn't want on an airplane. And take a swab. What do? They where it says sample there, that's the surface that you just swabbed, or the swab that came off the surface. You hit it with high energy, and the mass spectrometer goes ahead and breaks down these molecules, and they get bounced up into a detector, and you can find out if there's anything, gunpowder, explosives, things that shouldn't be on that luggage or ever. So think about that next time you go through the airport. If they do that, you can say, I know I can do that. Then they'll check you even more on that because you know. And this is another example, looking for pesticides on vegetables, fruit and vegetables. So what do? You take the fruit and hold it up, bombard it, measure what's there. So you can get a pesticide determination rather quickly, rather easily. So quantitative estimate of what's on the surface of that molecule. Pesticides, a nice example. This is just again a little different. So that's basically you see the beam coming down through the glass tip. This is just a little different where you're slipping the sample in from the side. And so the dry interface, well, that's just a dry system. You're holding it up and you're putting it in an energy beam, and you're doing the same kind of thing. You're going to blow off a number of things. It's a charge in there that gathers things it goes into and measures them. What's their mass? What's their quantity? And this, it's interesting that some of these methods will have many charges per molecule. When we do gas chromatography, mass spectrometry, liquid chromatography, mass spectrometry, we're typically looking at one charge per fragment, one charge, negative charge per molecule that you're measuring. And that's good. It makes life easier. If you get two charges, it complicates, but there is an advantage to having that complication and get maybe 5 charges per molecule or 10 charges. And so in that case, we've got a much bigger response to measure. And so if we want sensitivity, then we start looking at not putting 1 charge per molecule, but let's find that molecule, let's bombard it so it gets 5 charges. I got much more to measure, 5 times more to measure. And so it's again some really nice techniques in terms of forming ions, breaking our molecules apart to then measure and see what we've got. And that's where the mass analyzer comes in there. So we've got our ion source. How do we make ions? Okay, that's what we've been going through, how we make ions. And so how do we separate them ions? Because we want to measure, okay, what mass is it and how much do we have? What mass, how much? So always looking for this relationship. And magnetic sectors were the first uh, methods of doing this separation. I smile because I ran the mass spectrometer at Penn State University for my doctorate. That was where I was. And so we had a magnetic sector. And it is massive magnets because they need to do some really hardy work. And so I smile at that. Fortunately, they've gone by the wayside. But anyway, so they were the first ones. Again, it was like the picture we showed earlier about a magnetic sector. You've got an electric charge moving through a magnetic field. There's a right-hand thumb rule or something like this that says it's going to go this way, all your ions. But they're clumsy, they're slow, they're big. It takes some time and effort to charge a magnet, bring up its charge, drop its charge, and go back and forth. And so it's been replaced. So what we find most of the time now is what they call a quadrupole. And we'll go into what the quadrupole is, but it's just a different way of separating these, fragments that got blown into. That's the number one today. There's ion trap and time of flight. So we'll spend a little time, but not a lot of time with these other sources because the quadrupole really dominates the field. So this is what, again, like I say, I worked on. And so you've got your sample coming in over there on the right-hand side. Well, right-hand side as I'm standing. And gets blown to bits. And there's then a charge there that drags them out. So it may be negatively charged. You got a positive charge there, draws them out, gives them a velocity. They enter into this magnetic field, and you increase the magnetic field. So you keep on bending different molecular weight fragments around the corner to be measured here. And this is what it kind of gives you, something like this. At this mass, we got this many fragments. At this mass, we get this many fragments. So gives you this would be molecular weight of the fragments across the bottom. And so it tells you, what's the molecular weight of the fragments and how much of each of them. But a magnetic sector is, like I say, big and clumsy. It takes time, like I say, to charge that magnet up and down. And so really that hasn't gained or maintained popularity. It's gone by the wayside to things much simpler. Time of flight is one of the really good replacements. We've got one in our lab down in food science, but I don't know that it's been used in the last 20 years. Simply because the other alternatives are still really good. And so this is, again, in this case, where you do your ionization here, you've got your sample, see a laser beam comes in there. You put an electric charge to draw them out, so you blow it up and you get them going this direction. And what the mass spectrometer does, zap, how long did it take for this ion to get here? Oh, it must be this molecular weight. Bigger ions have slower velocities, so they come later. So you zap it and then see how long it takes for an ion to get down to be counted. So it's a simple technology, probably not that simple to come up with or make, but it is a simple principle. This is the one I don't have the foggiest idea how they do this. It's it's quadrupole, and this is the workhorse today. Almost all of the mass spectrometers you find are based on a quadrupole. And in this case, you again blow it up down here in your ionization source. So it's blown up and it focus the ions down between these four bars. And these four bars vary in electrical charge and electrical potential such that some molecules, like at the top up there, molecular weight of 100, for example, these are set up, these bars are set up so that only things of mass 100 make it through there. If they're 99, they go off at that direction. If they're 101, they go off in other directions. So it's basically focusing masses down this pathway to get to the detector. And it's, like I say, it's most popular by far, just because it works well. This ion trap is something, again, we've gone through. It's a development, and it hasn't really been competitive when it comes right down to it. So the ion trap is a way, again, of separating that big blend of ions that you blew up, how's that, or obtained by blowing up. And that's set up such that that ring, it has a charge, the bottom top plates have a charge, and they just keep these ions rotating. And if they change it in one way or another, that molecule escapes and you count it. You change it again, so you can keep on going through a series of changes that focus different molecular weight fragments down the table. They tend to work by the same detection system. So there's not much difference in, let's say, the ionization. You basically hit the molecule with high energy, and that energy just blows it apart. We differ greatly in how we separate those fragments by different instruments. And then, well, we're going to be separating one by one. We need something to measure them, and that's what we call our ion detectors. So that measures the amount of ionization that is coming out at different molecular weights. And this is a real benefit to us, or a good deal, in the sense that uses these dinodes here. So here we have our blown up bits and pieces coming in, and they hit that first kind of concave, and that molecule hitting there with a charge liberates more. So it goes from 1 to 2 ions. 2 ions go to 4. 4 get doubled to 8, and 16, 32. And so this is kind of this multiply. The more further you go, the more it's multiplied, the greater the probability you're going to see it and measure it. So this is the common detector that's used, and it's about as good as it gets theoretically when it comes right down to it. So it's good methodology. How to use MS identification interpretation. Every molecule has, its fragmentation pattern, what pieces it blows into when it gets electrical charge. So there is a difference in bits and pieces that you get when you bombard a molecule. And so by kind of counting how many masses did we get of mass 15, how many pieces of mass 15, or 27, 43, 58, and so on. Those tend to be the major ions. And so you simply need some way to count them and then get into a library that says, oh, this amount of this fragment, this amount of this fragment, and so on is from this compound. So that's what ties identity to this. High resolution, well, low resolution, that's our normal operation. When you go down to the department, we don't have a high resolution instrument, actually. They're low resolution. So it gives you a mass of unit mass. It says CH3 is a mass of 15. Well, it's not 15. It's 14.45 decimal places out. And so this, when we look at this one, the low resolution, basically, doesn't tell us what exactly it is. And so these fragments could be different compositions, and that's the interesting part. If we would have a high resolution instrument, then no, when we get that mass, it's going to come only from this combination of carbon, hydrogen, oxygen, and so on. This is the elemental composition. So that's really useful. First one, you can get these fragments in many different ways, but no, when you're high resolution, it can only be this molecule. Um, So that's you might say, why don't we run high resolution all the time on everything? Tedious, it's expensive, it typically isn't necessary. How's that? Because they are really expensive. To get that kind of difference in separating ability, you pay dearly for it. So we really have low resolution instruments. Um, Computer assisted searching, and that's always fun. You know, when you put a computer into a task and ask it to do a task, it'll probably do that task. Will it do it right? Well, that's another story. And so once you start, well, I think it's important you understand what you did, how you do it, and what to expect. Because if you simply say the mass spectrometer says it's this, I've been kind of look at you and say, really? How do you know? The computer told me so. Oh, really? Well, then this computer come around and okay, it may be wrong. And so again, use common sense. Is this expected? Is it logical? What other did you do? What other parameters do you have? Not just the mass spectrum. What other parameters do you have? Elution time off a gas chromatograph, elution time out of a liquid chromatograph. And so it does give you compounds, but it may be wrong. And that's the place where you come in very honestly and say, no, that's no good. There's something wrong with this. And anybody who takes the machine's answer without thinking about it is not in the right job. They're not. And so let's go on to this. So that's kind of the mass spectrometer in that part of it. And we want to have some way of separating a mixture so it goes into the mass spectrometer pure. So we'd like to say we've got 15 components. Let's separate each of those components. The MS just has to look at that compound, that compound, that compound. If they're running together, the compounds are running together. They're not separated. The mass spec is going to be a blend of whatever happened to be there. It's going to be a mixture. It's not going to do a good job of identification for you. It isn't going to tell you, oh, this is a blend of two or three things. It'll give you some silly answer again. And so the machine is not intelligent in a sense. And so we use chromatography to get our separations, the gas chromatograph or an LC. So liquid chromatograph, gas chromatograph. They are what we hope gives you a pure compound going into the machine one at a time. So HPLC, GC are used for that purpose. So the problem is then that you get these compounds, you want to give these compounds and you want to feed them into the mass spectrometer one by one. And so it's typically in some kind of a solvent. You know, if you're doing flavor work, you get a solvent extract of this blend. And now what's the most abundant volatile or solvent? You're not really interested in what your solvent is, you know that. And so the whole idea of getting some kind of a separation to go into the MS, and then oftentimes that's done by putting it in a solvent, and you make your injection into the mass spectrometer. What's the most abundant volatile? Solvent. Oops. You know, and so there's a bit of a problem because that little bit, maybe 1 microliter of solvent, expands to a tremendous volume. Oops, there went my vacuum. All of a sudden, my vacuum in the system just nosedive because of the solvent that just expanded and filled the instrument. So it doesn't seem like it'd be a problem, but it truly is. A microliter solvent can give you a very large volume. So your problem is how you separate whatever solvent system, whatever method you got, and have your compounds is extremely important. And so they also have to run under a vacuum. So whatever method you choose, it has to run under a vacuum. Um, operate it because it's operating at low pressure. The machine has to be operated low pressure. So there are some problems and or some challenges. This is the majority of what you find down our department. Um, so how many mass specs does Fernanda have at this point? Three, four, five? Uh-huh. And they're all interfaced with gas chromatographs. Yeah. Not, or do you have an LC in there someplace? You got an LC too. Yeah. And so this is the nice way to feed your sample into the system through a gas chromatograph. You do your separation, so one compound enters theoretically at a time into your mass spectrometer. So here's your GC, and this gets you into the mass spectrometer. Here's your ion source. So as a compound elutes, runs into this high energy, gets blown apart. The analyzer separates all of the pieces and puts them some kind of order. The detector measures them. So you get fragments, molecular weights, and abundance out of the system. For gas chromatography, that's not too much of a problem. That small amount of solvent. It's a very, very fine column, very small diameter. You're working with very, very low levels of solvent. In this capillary column, the comment here, 1 milliliter per minute. So at the end of your gas chromatograph to feed into the mass spec, if you have a flow of 1 milliliter per minute carrier flow, that's 10 to the 6 millimeter, 10 to the 6, sorry. Yeah, that is millimeters. So it just went up by a factor of 10 to the 6, the volume. So you put the solvent into the mass spec, and all of a sudden that expands in the vacuum. And there goes your vacuum, and there goes your system in terms of getting the data you want. So every one of these mass specs will have a really good vacuum system because it's not a problem necessarily of the mass spec, but it's simply the amount of solvent that your sample's in. That's the big pain in the butt. And so good vacuum pumps, yes, but there's also sometimes kind of devices that could do some concentration. And so this is looking at the MS system and what Fernanda would have. Although she probably wouldn't like to see that column. It's kind of a big column. She'd like to see that tiny, tiny column. It's 30 meters long. It's wound up over here. Looks kind of simple. But so you put your sample there, it goes ahead and it expands and turns into vapor, gets separated here. Theoretically, one by one, they come into your mass spectrometer. They go through your bars that do your not your fragmentation, but your separation one at a time. And you get something out on the computer. And so the system really works quite well, obviously. I've had a lot of time to do that. And these are some of the what I guess you'd see when you're out doing an analysis. So the orange one up here, so that's what the GC puts out. Says, oh, here's the peak, here's another one. Okay, we're going on our merit way. And one by one, of course, as they come out of the GC, they go into the mass spectrometer. And so the mass spectrometer is constantly bombarding that GC effluent and looking at what fragments are there and how much of those fragments are there. And one of the problems you have is ensuring that that's a pure compound. So is the GC doing its job? Can you guarantee it's doing its job? If you put in the mixture of two compounds into the system, the machine's going to get a headache. So you, just because you can't do anything with it. So it just turns into garbage. So here's peak 37 and peak 38. So there's two peaks that are running very close together. Fairly simple in terms of, or similar, I should say, fairly similar in terms of molecular weight there, a mass of 111. So what is that? but they're slightly different chromatograms. And so by looking at those fragments, like I say, you can measure a mixture without ever separating the mixture. So that's kind of interesting. Normally we have to separate things to measure them. Well, we don't have to separate them here. We go ahead and blow it into pieces and we look at pieces that are unique to each of the compounds that you want to measure. So the GC is kind of easy for us in the sense working with very low volumes of gas coming in. So it's not too hard to maintain a vacuum. Back in my days, we had big glass columns with granular material in it, and then it was a problem because we'd have 30 mils per minute of gas running into it. Here we're running maybe 1 mil per minute into the system. And so the problem is the system has to deal with some solvent, some carrier gas. It comes out of LC, so it'd be a liquid. So it might be ethanol, water. It could be any blend of solvents that are in there. And so the machine has to deal with very large volumes because, like I say, the liquids turn into large volume gases, and that's not true for GC. So kind of have to have a special system, and that's again where different mass spectrometers are well, different mass spectrometers are different. That isn't too helpful, is it? Anyway, but maybe get the idea. They're different, and there's a reason for them being different. And basically, what solvent systems they use and how they manage dealing with solvents. These are some of the specialized systems for doing the separation. Electrospray, thermal spray, particle beam. There's some opportunities or different methodologies, and we'll go through some of those. This is LC electrospray. That's probably one of the most common detectors that we use in the system. So here we've got our PSI nozzle. So your GC column would come down there, for example, and empty into there. There's about 4,000 volts of incentive to pick up a charge and explode. And so that comes through this kind of dotted region up here. And then there's also a place now where these ions go into the mass spectrometer for separation. So the kind of the atomization there, the fragmentation, breaking down into pieces, and then gathering those pieces to go ahead and do your identification from. How are we doing? 1 minute? Gosh, this looks like a good place to quit. Can I get show of hands? Quit? Oh, come on. The rest of you want to stay? I'm going. Okay. Anyway, have a good day. We'll pick up this point. Okay.